What are active components? Active components are the components which are able to supply energy to the circuit. What is an internal resistance? The resistance offered by the electrolyte is called internal resistance. Total current is equal to I1 plus I2. In parallel combination, current divides, and in series combination, voltage divides. Hello everyone, I am Maitri, Faculty of Physics, Vidhyaashram, Temple of Excellence, Mysuru. In this session, we will understand cell, and till now, in these 3 chapters, you have studied 2 components, that is resistors and capacitor. The resistor, which opposes the current flow in the conductor, and capacitor stores the charge. On the basis of their function, electrical components are divided into 2 types, that are active components and passive components. What are active components? Active components are the components which are able to supply energy to the circuit. So, components which supply energy to the circuit is known as active components. When these components supply the energy, then passive components absorb that energy or store that energy. You know, capacitor stores an energy. Therefore, capacitor is an example for passive components, or this passive components dissipate energy, that is loss in energy in the circuit. These components are known as passive components. Example for active component is cell. So, cell is an active component which supplies energy. Cell, batteries, diodes and transistors are the examples of active components. Then the example for passive components are resistors, capacitors, inductors, etc. are passive components. Now let us understand cell. So what is a cell? Cell is an active component. What is the functions of active component? The active component supplies electrical energy to the circuit. Here is the symbol of the cell. Cell has 2 terminals. One is positive terminal and another one is negative terminal. Always the positive terminal is represented by the longer line and the negative terminal with the shorter line, and 2 parallel lines. They represent the cell. Next, what is a battery? Battery is a combination of cell or a single cell whose circuit symbol is shown here. Combination of cell. Combination of cell or a single cell is known as battery. Yes, next. A very important term which is related to cell is electromotive force. By the name, you should not understand it as a force. Instead of that, it is a potential difference. So, it's not a force, it's the potential difference. The potential difference definition you have learned in the 2nd chapter, which is the work done per unit charge, or it is the energy per unit charge. This potential difference is electromotive force, which is abbreviated as EMF. EMF is nothing but electromotive force. Okay, we will understand this electromotive force by keeping the word, that is active component, as it is related to cell. Active component. What is an active component? The component which supplies the energy to the charge. So, that energy supplied to the charge is nothing but electromotive force. Yes, here is the picture. Look at the picture. A person. This represents with low energy. The person with a low energy, when he enters the battery, means here the person represents the charge. charge, okay, the charge with low energy, when it enters the battery, the energy supplied by the battery to the charge by the chemical reaction. And after this, it is moved towards the positive terminal of the battery from negative terminal. From negative terminal, the charge is moved to positive terminal. So, while moving, it gains the energy. That energy per unit charge is known as electromotive force. So, it comes out with the energy, high energy. That energy per unit charge is nothing but the potential difference. So, this potential difference of the cell is nothing but electromotive force. Understand this once again. So, instead of person, you consider a charge, the charge with low energy at negative terminal. When it enters into the battery, that charge is pulled or moved from negative terminal to positive terminal. While moving it from negative terminal to positive terminal, work is done by the chemical reaction. This work done is equal to the potential energy of the charge, supplied by the battery. That potential energy per unit charge is the potential difference of the cell, which is known as electromotive force. Now, let us consider this battery and we will connect this to a passive component. Here I have considered the resistor. So, you have to keep in mind or make a note that this electromotive force is defined when the circuit is in open state. Open state means no current is drawn from the cell. When no current is drawn from the cell, the maximum energy supplied to the charge is known as electromotive force. Now, the same battery is connected to a passive component. Example here is resistor. Now, here we have a closed path for the flow of charges. So, the current is drawn from the cell. When the current is drawn from the cell, the potential difference across the cell is known as terminal potential difference. So, what is terminal potential difference? The potential difference between the two electrodes of a cell when it is in closed circuit. To understand this EMF and terminal potential difference, let us consider another example. A charge which is at negative terminal is pulled into the battery and this charge is moved from negative terminal to positive terminal and work is done by the chemical reaction in this process. In this process, the charge gains energy of 10 joules supplied by the battery, and while moving from negative terminal to positive terminal, due to internal resistance of the cell, some energy in this is lost. Let us consider that lost energy as 2 joule per charge. How much energy is lost? 2 joule. Let us assume that 2 joule per charge the energy is lost due to resistance inside the battery. That resistance is known as internal resistance. What is an internal resistance? The resistance offered by the electrolyte is called internal resistance. So, due to internal resistance, the energy lost by the charge is 2 joule per charge. Now, what is the amount of energy left out for the charge? It's 8 joule per charge. This 8 joule per charge is available for the external circuit, that is for the passive component. This 8 joule is known as terminal potential difference. So, maximum energy supplied by the battery is 10 joule per charge, which is EMF is equal to 2 joules per charge is lost due to internal resistance of the battery, and plus the 8 joule is the rest of the energy for the charge, which is available for the external circuit, like for the passive component, that is known as terminal potential difference. Terminal potential difference. Now look at this. Look at this example. Always EMF is greater than terminal potential difference, which is denoted by the letter V. EMF is denoted by the letter E or epsilon, and terminal potential difference is represented by the letter V. So, always EMF is greater than terminal potential difference. Why? Because some energy is lost per charge due to the internal resistance of the cell. Now, from this example, we can give the relation between the EMF and potential difference, terminal potential difference. The relation between EMF and terminal potential difference, EMF is equal to 2 joules, right? That is IR plus terminal potential difference. I into R is the potential. Let us consider it as V dash, potential drop due to the internal resistance. Now, this is the relation between the EMF and the terminal potential difference, where small r is the internal resistance. Internal resistance. Now, the terms which are related to the cell you know, and so that we will consider the simple circuit and we will derive an expression for current in a simple circuit. Simple circuit is nothing but a circuit consists of a cell which is connected to a resistor of resistance R. And the EMF of the cell, let us consider it as E. And its internal resistance as R. Now, as this is a closed circuit, the current is drawn from the cell. Therefore, the terminal potential difference across the passive component or across the resistor is V. Across the resistor is V. Now, you know the relation between the EMF and terminal potential difference, or by the definition of EMF is equal to terminal potential difference plus potential drop due to internal resistance of the battery. Yes, EMF is as it is to the next step. Terminal potential difference across the resistor is given by I into resistance of the resistor, which is represented by the capital R, plus this is due to the internal resistance small r. So, the potential drop is given by I into small r, in which I is common. So, take I as common. In the bracket, we have capital R and a small r. And from this, or rearrange this to get the current expression for a simple circuit. The current expression for the simple circuit is E by R plus R. This is the expression of current in a simple circuit, where E is EMF, R is the external resistance, and small r is the internal resistance. And now let us understand the combination of cells. Combination of cells. Why we need to know the combination of cells? As single cell can't provide the requirement of the circuit, we need combination of cells where we can provide or obtain high voltage and supply more current. The first combination which we deal with is cells in series. And look at the diagram. We have two cell, first cell and the second cell whose EMF can be represented by the letter E or the symbol epsilon. So this is the symbol of the EMF of cell, or you can also represent it by E. So for the first cell, we consider the EMF as E1 and for the second cell as E2, which has internal resistance R1 and R2. The direction of current flow through these cells is from positive terminal to negative terminal. Inside the battery, you know that charge is pulled from negative to positive. Therefore, the direction of current flow inside the cell is from negative terminal to positive terminal. And this arrangement is series arrangement. That is, the current has only one path, single path through these two cells. Or you can consider this as an end-to-end connection. For this cell, yes, whatever you have written, you have to explain that. E1, E2 are the EMF of two cell. R1, R2 are the internal resistance of the cell. And I is the current in the circuit. VA at point A, VB at point B, VC at point C are the potentials at A, B, C. Yes. Next, find out the potential across the first cell, that is terminal potential across the first cell. The terminal potential difference is represented by the letter V, and it is between the first cell is between the point A and B. Therefore, you represent it as EB is equal to E1 minus IR1 by the relation V is equal to E minus IR. Same way, you find out the potential across the second cell, which is given by VBC is equal to E2 minus IR2. Now, the total, that is, if this two cells is replaced by a single cell and keep this here, it will be between point A and C. Now, the total potential difference between A and C for the combination is given by VAC is equal to VAB plus VBC, where you know the VAB and VBC, substitute that. VAB is E1 minus IR1 and VBC is E2 minus IR2. Yes, all EMF terms let us consider one side, and we can take the current as common and write the internal resistance in the bracket. In the next step, VAC is equal to E1 plus E2 minus, in this two term, minus I is common, and in the bracket we have R1 plus R2, and consider this as equation 1. Yes. Next, this series combination of two cells is replaced by a single cell whose EMF is E equivalent. EQ represents equivalent to that two cells, and its internal resistance is Req. So, the two cells which are between the points A and C is replaced by a single cell between the same 2 points. That single cell is known as equivalent cell, whose EMF is EEQ and internal resistance is REQ. Now, for the single cell, what is the terminal potential difference? The terminal potential difference V is given by EEQ minus IREQ. Consider this as equation 2. And from equation 1 and equation 2, yes, here is the equation 1 and this is the equation 2. Let me write the equation 1 here. VAC is equal to E1 plus E2 minus I of R1 plus R2. This is equation 1. Compare the equation 1 and 2. Compare it. In the place of EEQ, what we have in equation 1? We have E1 plus E2. Therefore, equivalent EMF of combination of two cells in series is given by E1 plus E2. Same way, compare and find out REQ. In the place of REQ, what we have in the equation 1? We have R1 plus R2. So, equivalent internal resistance of two cells in series combination is given by R1 plus R2. This is the expression for the equivalent EMF and equivalent internal resistance in series. If I have n number of cells in series, then E equivalent is given by E1 plus E2 plus so on up to n cells EMF. Same way, internal resistance is given by R1 plus R2 plus so on up to n cells internal resistance. Now let us consider the cells in parallel, the second combination. Cells in parallel. We can arrange the cells in series or parallel. This arrangement is parallel arrangement, where the first cell has EMF E1 and internal resistance R1, and the second cell has EMF E2 and internal resistance R2. The current through the cells is I1 and I2 because the current has two paths. So, the current divides here and flows through the two cell. The current we will consider in the first cell as I1 and to the second cell as I2. Yes, the same symbols you have to explain. E1, E2, EMF of the two cells, R1, R2, internal resistance of the cell, I1, I2 are the current in the circuit. And what is the potential difference across these two cells as they are connected between the same 2 points? The potential difference is V, which is same for the two cells because they are connected between the same 2 points. So, potential difference V is between the 2 points, same for the two cells. Yes. Here, the quantity which divides is current. So, total current is equal to I1 plus I2. In parallel combination, current divides, and in series combination, voltage divides. Yes, by that, the total current I is given by I1 in the first cell plus I2 in the second cell. Consider this as equation 1. Then we will find out the potential difference across the cells. Across the first cell, the potential difference V is given by E1 minus IR1. Same way across the second cell. Across the second cell is given by V is equal to E2 minus IR2. In this two equation, let us rearrange that in terms of current. Then I have I1 as E1 minus V by R1 and I2 as E2 minus V by R2. Consider this as equation 2 and this as equation 3. 2 and 3, let us substitute in equation 1. Then I is equal to, this is I1 plus this is I2. Yes, I1 and I2. Now let us simplify this. What we have is I is equal to E1 minus V by R1 plus E2 minus V by R2 after substituting 2 and 3 in 1. Let us simplify this by taking LCM as R1, R2. Then in the numerator you have E1 minus V of R2 plus E2 minus V of R1. Yes. Multiply this R2 into the bracket, same way R1 into the bracket. Then I is equal to E1 R2 minus V R2 plus E2 R1 minus V R1 divided by R1 R2. Let us cross multiply this. Then I of R1 R2 and all the E terms one side, E1 R2 plus E2 R1. Now in this two terms we have minus V as common. So minus V of R1 plus R2. Yeah, this is the equation. But we need in terms of V. So let us consider this V towards the LHS and I towards the RHS. Yes, then V of R1 plus R2 is equal to E1 R2 plus E2 R1 minus I of R1 R2. Yes. And we need only V in LHS. Therefore, consider this R1 plus R2 into the RHS numerator. Then V is given by, V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I of R1 R2 by R1 plus R2. Why did I represent this equation in terms of terminal potential difference? Because the two cells which are in parallel are replaced by a single cell whose equivalent cell is given by, equivalent cell EMF is given by E equivalent and internal resistance is given by R equivalent. And across the single cell, the terminal potential difference is given by E equivalent minus I R equivalent. Consider this equation as 4 and this equation as 5. Now compare. For the comparison, we need the equation in terms of terminal potential difference. Now comparing this, in the place of E equivalent, what I have is E1 R2 plus E2 R1 by R1 plus R2. This is the expression for the equivalent EMF in parallel combination. In parallel combination, the equivalent EMF is given by E1 1 R2. Observe this. If you write 1, then for the R you have to write the next number, that is R2, and E2 R1 by R1 plus R2. Compare and find out what is the expression for the R equivalent. The expression of R equivalent is R1 R2 by R1 plus R2. So this is the equivalent EMF and equivalent internal resistance of two cells which are in parallel. So in this session, you have understand what cell is and the combination of cells. In the next session, we will understand the Kirchhoff laws and very important question, that is balanced condition for Wheatstone network. Thank you.